Okay. So this is will be a very unusual talk in the sense that I am stuck in an airport and I couldn't find an airport lounge. So, and I forgot headphones. So there will be noise around and I don't know. I think a lot of different workshops and conferences had been holding off for a while and then scheduled all these conferences around this time. And so it's busy time. I guess before I begin, I'm wondering about you guys. Where are you mostly math majors or in math departments?
That's a good point. Like basically one third are undergraduates, 1/3 are graduates, and 1/3 are postdocs and faculty. But how many people are math major or co-major? So, oh, lots of them. How many people are computer science majors? Some of them. So does that give you some idea?
Sure. And then my next question is, because it's an unusual situation, would you rather I go ahead with this talk, or I can also just have like an informal Q&A if you have questions? I don't.
I think we'd rather hear this talk. Speaking for myself, we're eager to hear your talk on this topic.
Okay. Okay. So then, so the aspect of machine learning that I've been focusing a lot lately on is the optimization aspect. And so how many of you are familiar with gradient descent? Gradient descent, okay. How many of you are familiar with stochastic gradient descent? Okay, have you been learning about that in the workshop so far?
No.
Okay, okay. So then that's great. So then I'll go over that part now. So the topic of my talk is stochastic gradient descent, where optimization meets machine learning. So the motivation is neural networks, which I'm sure that you have learned a lot about in the workshop, are from the perspective of optimization. They're just functions of a particular parameterized form, and they're modeled after the human brain. And they either interpolate or approximate a set of training examples in the supervised setting of machine learning, which I'll be focusing on. So we have a lot of training examples. Here we have little n for the number of training examples, and each xn is an image or a word or some data point, and the y is a label for that point. And so why are neural networks in particular so powerful and versatile? Why are they everywhere now when they weren't, say, 20 years ago? So I'd say two main points here. One is this particular parameterized parametric form of functions are very powerful, have very powerful approximation theory properties, and they're non-linear, highly non-linear, but still very simple, simple form. So simple that they pair very well with very simple optimization methods like stochastic gradient descent, which can be implemented at a very, very large scale, and goes very well with modern computer hardware, in particular GPUs. Enable for like stochastic gradient descent is very efficient communication-wise, memory-wise, arithmetic complexity-wise. So where do we stand regarding theory versus practice of stochastic gradient descent, or as I say, SGD? So just to get a little bit more into the weeds of it, a sort of good example or typical example of a neural network optimization problem is we have a class of, we have a loss function, which in the supervised setting and in the regression setting is often just a nonlinear least squares function. So it's a function of the weights W, and the weights come in the form of a sequence of basically matrices and then offsets B. And so these are the variables we're going to optimize over. So we want to find a best set of weights which fit the training data. And the L2 loss is very popular because has a nice, the derivative has a very nice form. And so a typical kind of neural network function, say of depth D with a ReLU activation function, has this form, which is a composition of just the simple element-wise nonlinearity. A ReLU nonlinearity is just element-wise the max of the input scalar and 0, composed with these parametric weight matrices, and we're going to optimize over the weights. And so you plug this parametric function form back up here into the least squares loss function, and then you get an optimization problem. How do we solve these optimization problems when little n is in the order of billions, when the size of the training data, xj, are images, which are order of millions or hundreds of millions, and when the number of weights, p, basically the number of entries, total entries, if we regard these weights as one long vector, when p is also on the order of billions. So there are 3 different dimensions that are giant. This is a very large scale optimization problem. How do you solve, try to minimize a function of this form when it's you're at this scale? At this scale, most of the optimization methods you learn about, like Newton's method, linear programming methods, second order cone optimization problems, you just can't work. They're too expensive or complicated and a little bit too brittle to noise. Even simple gradient descent, where you just iteratively compute, evaluate the gradient of this function you want to minimize and then move some direction in the negative direction of the gradient at that point, even simple first order iterative methods are too expensive because computing a gradient is too expensive. So stochastic gradient descent is sort of the method of choice for optimization in training neural networks, not just in training sort of the old school supervised fully connected neural networks like I presented on the previous slide, but really in training, the stochastic gradient descent really has persisted as the optimization problem, even as neural network architectures have changed dramatically over the last 10 years. So neural network architectures, or the type of parametric function classes that are most powerful, have been changing from convolutional neural networks to GANs, generative adversarial networks, to most recently transformer networks. And even as these parametric classes have become more and more complicated, stochastic gradient descent has remained sort of the backbone optimization problem for these reasons I mentioned. The basic stochastic gradient descent algorithm is very simple to explain. If we want to minimize a loss function f, which has a finite, I'll just wait a minute. If we want to minimize an optimization problem with a finite sum form, can you see this cursor?
Yes.
Okay, so it just has this is just a finite sum form. In neural networks, you often want to minimize a function with this finite sum form because for each I, this is a component corresponding to the training example I. And these finite sum optimization problems often involve n, a number of training examples, which is really huge. And so a very simple observation, when little n is very large, computing even a single gradient of such a function at a particular vector, at a particular point w, is costly. It's cheaper by a factor of n to compute the gradient only of a single component function, fi, just by linearity of the gradient, right? So you see that by gradient of the left-hand side is equal to computing, little n of the gradients of the right-hand side. And so if we have redundancy, if we have reason to believe that, we can probably get away with, instead of computing the full gradient at every iteration of gradient descent, but instead just draw a small number of indices I at random out of n, and moving in the direction of the negative gradient of the average of that little random mini batch of components, then that generates the stochastic gradient descent algorithm. It's a randomized approximation or surrogate for gradient descent, which in the simplest setting, you initialize a number of step sizes that you're going to move at each iteration of the algorithm. You have an initial guess of the parameters, the parameter vector w, that you're going to try to find an optimal set of parameters, but you start with some initial guess, usually a Gaussian random vector. And then until convergence, draw a random index from the total number of components n, and simply move, do a gradient descent update, except update your weights according to moving step size eta t in the direction of the gradient of that one component in the finite sum. Or more generally, the gradient of the average of a randomly selected subset of batch size B out of the N. And so this is just like a sample of what a trajectory of stochastic gradient descent might look like if this represents the loss surface of, say, a quadratic loss function. So if this is a very simple quadratic, the level sets look like these nice ellipses, and stochastic gradient descent will sort of move around. And if the step sizes eta don't go to 0, but just go to some small finite number, then stochastic gradient descent will go and sort of bounce around in a good basin around a minimizing point. And in machine learning applications, often getting close to the global minimizer is good enough. Not minimizing it exactly, that's not so important, getting just close enough to a good point. And why is that? Why in machine learning applications is it often okay to just get close to a good set of weights? Because in machine learning, this optimization problem here is not really the end goal. The end goal isn't to optimize this loss function completely. The end goal is to apply, to use the set W star, a good set of weights you get from this, in generalization to make predictions on training data or to data that you haven't used in the training data. So this is an empirical risk minimization. Some say that even finding a W star that's not the exact minimizer of this will do better in generalizing or making predictions on unseen data points. But that's a separate topic from optimization. So I'm not going to go there too much, except this is stochastic gradient descent. Does anyone have any questions?
I think we're okay.
Okay. So stochastic gradient descent, everyone links it with neural networks because it's the backbone of optimization in neural networks, but it has several roots before neural networks. It sort of appeared first by Robbins and Monroe in 1950 as stochastic approximation. And the motivation there was just to solve for roots of functions where we don't have exact evaluations, but we have a random variable instead. And so I won't go too much into the details here, but an important extension in the 50s was to extend this from a univariate function, a univariate setting to the high dimensional setting. And because Bloom realized and others realized that this sort of simple stochastic optimization could be particularly powerful in the high dimensional setting. And they showed convergence of stochastic gradient descent in expectation, actually with probability 1, provided the step sizes that one sets at the beginning are somewhere between being summable and being square summable. So think of like a decay rate between 1 over j and 1 over square root of j. Some decay rate in between those is a good sort of step size schedule for theoretical convergence under nice settings like smoothness and convexity. These are nice settings. Another independent line of work that sort of I think of as a predecessor to stochastic gradient descent was the Kaczmarz algorithm. There was no randomness in the Kaczmarz algorithm, but the Kaczmarz algorithm suggested to solve systems of linear equations by just cycling through the rows of the matrix in the least squares problem one's trying to optimize, cycling through the rows in a certain order, and then updating a solution vector for the least squares problem by what's essentially, moving in the direction of negative gradient of just that row. And in this setting, the step sizes aren't a problem. They're sort of a good natural choice of step sizes that's hidden here. So this was cyclic optimization. So this was no randomness, but and this is connected to the Institute for Advanced Study, where von Neumann was, and doing lots of important theoretical work in Banach spaces and analysis. And von Neumann extended, independent of Kaczmarz, this sort of cyclic projection method where you cycle through a number of simple sets where you want to find an optimization point in the intersection of them. And he proved a nice convergence rate for the projection onto convex set setting in the set of two convex sets. Whereas, going through these rows and Kaczmarz can be thought of as having n convex sets. The sets are just affine subspaces. Okay. In fact, it's really hard to extend von Neumann's analysis from two convex sets to a general number of convex sets if you're limited to going through the sets in a cyclic order. The key to breaking out of that difficulty to be able to analyze these sort of iterative projection methods is to introduce randomness and say, I'm not going to try to even prove things with probability 1 anymore. I just want to prove convergence rates in expectation with respect to the draw of the random order. And so that was a big sort of change in mindset over the past 50 or 60 or 70 years after von Neumann, where mathematicians became more comfortable with randomized algorithms and small probabilities of failure because they work better in practice often, and because they're easier to analyze, because computing the expectation of a bunch of complicated decision choices is easier than proving a sequence of deterministic complicated decision choices. And so this is just sort of a background. The Kaczmarz method became implemented in practice as the algebraic reconstruction technique. It was very useful in the first medical scanners because it's so simple to solve a least squares problem when you just cycle through solving gradient updates row by row. It was simple enough to be implementable in a medical scanner. And then later in the past 10 or 15 years, Stromer and Verschienen introduced the randomized Kaczmarz algorithm, where we have the randomness involved, where we sample rows with certain probabilities proportional to the norms of the rows in such a way that one can prove a very sharp rate of convergence of the method in expectation to a solution of the least squares problem. And so this is sort of the result they gave, and it's sort of the natural extension of the types of convergence rates one has for deterministic gradient descent, but in the stochastic setting. Notice this is an expectation instead of a deterministic result. Okay, so stochastic gradient descent is one can extend the convergence theory of the randomized Kaczmarz algorithm to more general optimization problems having this finite sum form, which arise in machine learning. So in the case of solving linear systems, that corresponds to these little component functions, fj being just a quadratic function whose gradient can be computed explicitly. But you can extract sort of what are the important qualities that we need in these components in order to be able to have a more general theory of stochastic gradient descent. And the nicest conditions one can ask for theory are that each of these component functions is convex. The loss function f, so the average, or when you put all of the components together, the loss function is mu strongly convex, meaning that there's a quadratic bowl that's like a lower bound globally on this function. There's some lower bound quadratic with curvature mu, more or less. Each component function is a smooth function, and its curvature or the rate of change of the gradient of each component is bounded above by some L, some good gradient. And all the component functions share a minimizer. So this is that there exists a point in the intersection of the convex sets, which correspond to the affine, which correspond to the subsets where the gradient of each of the components is equal to 0. So if the components are convex, these levels, these sets are convex. And so we're back into the finding a point in the intersection of a bunch of convex sets. So this is the setting basically where one can prove really nice convergence rates for stochastic gradient descent, which extend the randomized Kaczmarz convergence. And they just show that the rate of convergence of stochastic gradient descent really depends on the condition number of the optimization problem. What's the condition number of an optimization problem? In this setting, it's pretty well defined. It says like basically the maximal smoothness L, the smoothness parameter L divided by the strong convexity parameter mu. And this just extends the notion of the condition number of a matrix, which is the maximal singular value divided by the minimal singular value. So the better conditioned the optimization problem, the faster stochastic gradient descent will converge. And so, loosely speaking, a lot of engineers who are doing neural network training and practice, what they're doing is they're applying a lot of data pre-processing techniques and a lot of transformations of the loss function for the particular problem they have to make the loss function for that corresponding optimization problem better conditioned, to make its landscape look more regularized, so that the stochastic gradient optimization will have faster convergence. So a lot of the engineering of neural network training these days can more or less boil down to making this the optimization problem that one's going to try to solve better conditioned, to look less irregular, to sort of improve the global curvature and so on. Now, a funny thing is, so you might think that theory that I just talked about is very ideal. We're talking about convexity, we're talking about smoothness. This seems very different from the setting of neural networks and machine learning, where I told you the parameterized loss function is a composition of non-linearities, so it's very non-convex at first glance. But in fact, in lots of the modern settings of neural network training, these complicated parameterized classes of neural network functions actually behave like they are approximately convex locally. And that is because when neural networks are overparameterized, meaning that the number of parameters W that one's optimizing for is larger than the size of the data set, the number that's sort of larger than N times D, which is the number of basically the size of the training data. That means you're sort of lifting the optimization problem into a very high dimensional space, implicitly lifting. And when you have an optimization problem that's non-convex or nonlinear or complicated in sort of a lower dimensional space, and you lift it up to higher dimensions, it simplifies. It becomes more regular. And so in the overparameterized setting, applying stochastic gradient to neural network optimization often looks a lot like applying stochastic gradient descent to a sum of convex smooth functions. And so this is just a typical plot of this sort of behavior, where we see sort of we watch how the function values change with the stochastic gradient iterations, and it looks a lot like what one sees when applying stochastic gradient descent to quadratic functions. And so this is sort of the overview so far. We have a good understanding of theoretical guarantees for stochastic gradient descent under conditions of convexity and smoothness. And then we also understand now a big push in the neural network theory is understanding how, with overparameterization and random initialization, training neural networks, which are mathematically, non-convex, non-linear problems, are approximately, when one takes a few reasonable approximations are approximately nicely behaved optimization problems. And so in practice, we see the theory that we have for stochastic gradient descent actually informs practice, and practice reflects the theory in certain regimes. And with this overparameterization, another issue, which I'm not going to talk about, is that basically there are many choices of parameters which exactly give global minimizers for the loss function, because you're in an interpolation regime where you're interpolating the training points exactly. And stochastic gradient descent and gradient descent tends to have the behavior of converging to one of those minimizers that's a good minimizer, like a low complexity minimizer in some sense, maybe smooth or sparse. And so this is what's called implicit bias of an algorithm. And so a line of theoretical work is understanding in a more general sense what the implicit bias of gradient descent or stochastic gradient descent is. Why do these algorithms tend to converge to minimizers that are good rather than minimizers that are bad? So let's see. So I just want to say that the particular work that I've looked at a lot is making stochastic gradient descent less hyperparameter dependent. So stochastic gradient descent has a lot of hyperparameters. Hyperparameters are variables in the algorithm that have to be set to certain values in order for the theoretical guarantees to hold that I told you about. And these values that you have to set them to are often values that are not known in practice. So an example of this, what you see here with this picture, is that if we have this nice loss function, this is about as nice of a loss function as you can have. It's just a quadratic function here. Stochastic gradient descent, just like gradient descent, if you set the step size parameter, eta, if you set the step size too small that you move in, then you'll converge, the iterates will converge, but they'll converge very slowly. And so often in large scale machine learning, you can't afford for the algorithm to converge too slowly. Training time, is speeding up convergence is very important. So converging too slowly is not acceptable. And if you set the step size to be too large, then the stochastic gradient won't converge. If you set it too large, it'll bounce around or maybe even bounce out of a well like this, and it won't converge. And so stochastic gradient descent, it's sort of like the trade-off. The trade-off we get for how simple it is. We can go to large scale problems, but the trade-off is that it's very sensitive to hyperparameters. The step sizes are like the most basic hyperparameters in the algorithm. When we're talking about gradient descent, we don't have to worry about step sizes because there are principled ways of adaptively at each iteration of gradient descent finding a good step size parameter that's only incurs like a logarithmic number of queries to the function at each iteration. These are called line search methods. And so the problem of hyperparameters and deterministic gradient descent is essentially a solved problem. But when we add in the randomness, the stochasticity and stochastic gradient descent, all of these methods that work for deterministic gradient descent don't extend because they tend to overfit the directions that are random directions in stochastic gradient descent. And so they just don't work. So making stochastic gradient descent or adapting the algorithms, making enhancements to stochastic gradient descent that are robust to hyperparameters is a very active area of research, and it's very interesting. And so in practice, what you don't really see when you you see these examples of I don't know, apps or something where a neural network has been used to do something like transform a picture into artwork or to do voice recognition or so on. What you don't see is that before a good set of weights was found in the parameterized model that is used in that model that does good prediction, someone was manually experimenting with lots and lots of different choices of step sizes to use in stochastic gradient descent in order to get the neural network, the training algorithm to work, in order to get the stochastic gradient descent to converge to a good weight vector. Someone had to play with good choices of step sizes in order to get the stochastic gradient descent algorithm to converge at all. And as we move to more complicated neural network architectures, they become, in some sense, more and more sensitive to these step sizes. And so it becomes more and more of a complicated issue to find a good set of step sizes that gets the stochastic gradient to converge to a good point. In practice, one experiments with many different sort of piecewise constant decaying step size schedules. So we want the step sizes in stochastic gradient descent to decay to 0 because we want these iterates that start bouncing around. We want them to eventually hone in closer and closer on a good point. And then we want to decrease the step size so that the variance is reduced and it converges to a point estimate. That's generally what one wants. But at what rate do we decrease that variance? At what rate do we drop the step size? You see when the step sizes are dropped, that stochastic gradient descent, it acts like a helicopter. Imagine a helicopter sort of zooming over a landscape. So the helicopter starts up very high in the sky, so it can see a lot of the landscape, and then at some point it drops, zooms in when it sees a valley or something, and then sort of hovers around at a lower altitude for a while, and then eventually gets a better view and drops closer and closer and closer until it lands, say, in the valley of the landscape. So getting that step size schedule is somehow like scheduling, finding a good way to sort of hover and drop to get close to a good set of weights. This whole process is not completely, but it's very ad hoc. It takes weeks of a human being manually tuning different step size. It costs millions of dollars in GPU time. It's very costly and expensive. And so somewhere where mathematicians can come in is develop new mathematics, new extensions of stochastic gradient descent, which automate this process of eliminating hyperparameters. And an interesting area that's starting in that direction are adaptive gradient variants of stochastic gradient descent, where the step size is sort of treated as a parameter, not a hyperparameter, a parameter that's optimized along the way with the algorithm. Mathematically, this is interesting because treating the step size as a parameter to optimize along the way is very nonlinear. It's a very nonlinear dynamical system. And so it becomes complicated to understand dynamical systems. But the simplest form of this is to, instead of a priori initializing a set of step sizes and then running stochastic gradient descent and then starting over again if those step sizes didn't work, is just initialize one step size parameter and one b naught, which is a very small number, like 10 to the negative 6, just a scalar number. And then sort of update this b along the way of the stochastic gradient estimate by basically accumulating averages of the L2 norm squares of the stochastic gradients one sees so far. Think of the law of large numbers or the central limit theorem. These are stochastic, these are random vectors, and we're just sort of averaging, accumulating in a certain way, the sum of the squared L2 norms of these random vectors. And then using this sum, using this accumulating sum as a surrogate step size in the t plus first iteration of stochastic gradient descent. So if the stochastic gradients are too large, indicating that we're not converging, this BT parameter will get large. And when we take 1 over BT, we'll be effectively decreasing the step size. So if the gradients are too large, this will automatically decrease the step size so that we converge. So this is a random variable. So this is just a different kind of stochastic gradient descent algorithm with the step size treated as a parameter that's being updated along the way. And so this is called ADAGRAD in the literature, this update. And what we were able to show is that this ADAGRAD algorithm will always converge. So where gradient descent or stochastic gradient descent can bounce around and escape if the step size is too big, ADAGRAD will always automatically correct for that situation and decrease the step size at a rate such that stochastic gradient descent will converge. And so I know this is a bit too high level, so I don't worry about this, but the innovation is that using some new techniques for analyzing these stochastic gradient methods, which can deal with the setting where the step size is itself a random variable that's correlated with the stochastic gradient direction, we can prove convergence of this sort of adaptive gradient variant of stochastic gradient descent. And the convergence, rate is not contingent on setting a step size schedule correct in advance. It just always converges, and in the best situation, converges at the same oracle rate of stochastic gradient descent, as if we had set the step sizes and stochastic gradient descent just right, using information that's not available in practice. So what this is like a first step towards making the optimization algorithms used in neural network training and large scale machine learning less sensitive to hyperparameters, so that human beings don't have to spend weeks of time fiddling with these parameters, spending GPU compute resources to do this, and also to make machine learning more automated, so that we can operate and train neural networks online, not offline for weeks to figure out the right hyperparameters and then deploy it to the customers, but really online and in low power situations like on customer cell phones. So because we want to make training neural networks less computationally expensive. And there's really interesting math involved in proving these types of theorems involving nonlinear dynamical systems, martingales, understanding when you have products of random variables that are correlated with each other. And so I guess I just wanted to convey that this is an area that I think has important practical implications, just in terms of using less of the world's energy, which we have so little of, for training neural networks. Let's instead use that energy to, like, I don't know, do good things with the planet. And to do that, we're trying to make the optimization algorithms used in neural network training and so on more democratic, in the sense that they're only confined to training in large corporations which have the money and resources to have all the GPUs. We want anyone in the world to be able to train neural networks or to do predictions with machine learning without having to have access to that. So that's my talk. Thank you very much for listening to this.
Thank you. Really beautiful talk. So do you have time for a few questions, or are you off to your net?
I have plenty of time. Time is not my problem.
So questions about the talk, or just questions, in general about how Rachel got to the research direction she's engaged in now? Questions? Good.
So you spent a lot of time on adaptive step sizes, and I'm curious whether similar attention has been paid anywhere to something like adaptive batch sizes, like changing the level of stochasticity.
Yeah, absolutely. That's another very, very important parameter, hyperparameter in stochastic gradient descent. It's not unrelated to the step size. But yes, there's also another important direction is changing the batch size. So the larger mini batches in stochastic gradient descent corresponds to smaller variants of the stochastic estimate. So finding a good mini batch size just corresponds to number of indices sort of drawn at a time here. There's a sweet spot where the mini batch size is too big, then it becomes like you're spending too much effort to compute that mini batch gradient. If it's too small, then the variance here is too large. And so what one really wants to do in stochastic gradient descent is often start with small mini batch size at the beginning. So when you're far away from an optimal solution point in your landscape, who cares if there's large variance? Because you're so far away, all of the indices, all of the component gradients all kind of point in the right direction because you're so far away. So what really works best is to start the stochastic gradient descent with small mini batch sizes, and then increase the batch sizes as you get closer to a solution and you want less variance. You want to get, again, to hone in closer and closer on that solution. So yes, so scheduling larger and larger mini batch sizes is another thing. I've been thinking about it, and I think that we'll see some interesting mathematics there in the next 5 or 10 years. But I think so. The answer is yes. It's a great question.
Other questions? Jamie?
Hi, Rachel. So when you're thinking about these adaptive step sizes, you're like kind of, in my mind, adapting to the objective landscape. Yeah. And I was wondering if you thought at all about trying to use this kind of idea to adapt to things like untrustworthy or like adversarial gradient samples.
Absolutely. That's a great question. So right. So I presented a sort of simplified version of this adaptive gradient algorithm where we just have one scalar parameter, BT, that we're updating along the way. But one could also consider updating several of these parameters for, say, different batches of these components. And one thing about adversarial types of examples or outlier in the training data is that they're going to tend to correspond to gradients that are larger in magnitude because they're outliers. So maybe I change the subject to outliers, but maybe I'll get back to adversarial. Outliers are easier because outliers are training data points that don't really fit in with the rest. And so when you if you choose those training data points in a mini batch, the gradient, the gradient's going to be larger because you've been trying to fit the good training data points, and then suddenly you draw a mini batch of these outliers, and so the gradient's going to be large. And so you can use these adaptive gradient methods to detect points in the training data set that seem like outliers in the sense that the value of the loss or the magnitude of the gradient tends to persistently spike up when evaluated at those points. And so adaptive methods can be used to detect and try to remove outlier points. Adversarial points, though, that's harder because if you're talking about an adversary who can pretend, to like trick you by making, so maybe, were you thinking of outliers or something else?
No, that was great. Yeah, outliers.
Okay. Yeah, but that is definitely, so adaptive methods for outlier detection. And that's something that at least I'm working on. So probably other people are working on that too, because that's really interesting.
Thanks.
Other questions? So could you just give a brief description of like what your thesis was and like how you got here from there?
Oh, sure. So I got my PhD from Princeton in 2009. I was working with Ingrid Dobeschies in the computational and applied math program. My PhD was in the area of compressed sensing and signal processing. Compressed sensing is, there was a topic, I think there was a Women in Math topic on compressed sensing maybe a decade ago when I was there last, but it's concerned with finding sparse solutions to linear systems. And I learned a lot of the sort of random.
Welcome to our 10-minute Los Angeles. We will do 10 minutes. If you can have your boarding passes and photo identification available for presentation to us when we start the board, that would be appreciated. In the meantime, I am looking for the following Los Angeles guests and passengers. If you hear your name,
I'll just keep talking. I don't know if you can hear me. This is going to go on. I learned a lot of the random matrix theory that actually translates a lot to the theory of understanding stochastic gradient descent and optimization.
Showtime will also be playing a couple of Transport Canada.
Hear you.
So again, these are pre-recorded, pre-boarding announcements. When we just start the board, you'll hear my voice and I'll
Yes.
when we start boarding by its own number.
Louder than the announcements. You can keep
Yeah, Rachel, you can keep talking unless you have to. Listen.
Okay. Okay. And then and then let's see. So compressed sensing, I started later in my postdoc at NYU, working on randomized algorithms for numerical linear algebra. So sketching large, low rank matrices, taking these matrices and hitting them with a small number of Gaussian vectors and talking about how one can get a low dimensional sketch of a large low rank matrix, which preserves sort of the spectrum of that matrix. And this is important because you're working with matrices that are so large you can't even store them. So I went from compressed sensing to randomized linear algebra to then later on as faculty at UT, I got more interested in the machine learning and optimization aspect, and stochastic gradient descent I sort of studied before it became blew up as being important in neural networks. My first paper on stochastic gradient descent, that's now my most well-cited paper, it was rejected several times because we were told, what's the point? And then like the usefulness of stochastic gradient descent in neural network training sort of became apparent later. And I'll just say, like, people now understand the point. So that's just, I guess, a story I threw in to tell you, if you are working on something, you think it's interesting, you think it's important, you think it has value, you probably know better than other people. And so, often you might encounter resistance early on, but later on it will catch on, and you just had the better intuition at first than they did.
Other questions?
I have a question.
One more?
Yeah, so one of the biggest assumptions in SGD is that you need to have bounded variance in the gradients, right? You can't have your sigma or grad FI cannot be true as large variance.
Well,
it appears in the bounds, right?
actually, we in a paper this year, so that's not always the case. And in a paper this year, we were able to remove that assumption. And so we don't need bounded
but you need control over it, right? Like you need some control like that. My question is, that doesn't hold for, say, an RL setting where the variance is so large, like you can actually like literally diverge for anything. So do you see a way of adjusting it so that you can remove any assumption on these like variance? Or how can you adapt SGD to handle that it doesn't go to regimes which have high variance in their gradient?
So so you're right. So training neural networks in the reinforcement learning setting, you see SGD is much more sensitive, and often it's just hard to get it to converge at all. Now, these sorts of requirements that the gradient, we have like an affine variance bound on the gradient where the variance doesn't grow faster than, say, the norm of the gradient of the average function f. They're sort of required. This is sort of like a necessary condition for the types of convergence guarantees one needs in stochastic gradient descent. And so I believe something one might have to do there is like really a new
flight 8738 to
Keep going.
new methods of understanding behavior in average case settings, where you have to understand how to get, like you said, to certain regions of the landscape where we have some sort of boundedness of the gradient. there will be regions where there's none, but there have to be regions where there's good control in order to get convergence at all.
We will start with for zones 1 and 2.
So one sort of add-on to stochastic gradient descent that's very helpful in practice is called batch normalization. And batch normalization is sort of a hybrid of adaptive gradient methods and
we thank you for your cooperation.
Some reshaping of the loss function. And it's very helpful for making stochastic gradient descent converge in the reinforcement learning setting. And we don't understand why. And so I think people will start to understand batch normalization more in the next few years.
Do you think batch normalization is just that you're normalizing the data matrix so that it has like a nice mean and a nice variance after every prelude, etc.? And then you just apply some sort of, you're in the average setting of a high dimensional random matrix, which is normalized, and then you can just convert it because everything is being zero and nice variance. That your take on batch normalization?
I'm really sorry. I'm having trouble hearing that. I'm so sorry about this. I heard some things that sounded right.
Okay. So that was, Rachel, that was Courtney Paquette, so she can maybe follow up with you.
Oh, hi, Courtney.
Hi. Sorry.
What are you doing there?
Well, what do you mean?
You're like an esteemed faculty.
If you're coming to the random matrix theory, are you coming to the other conference, the Tom Jogden conference, or I'll be there?
I'll be there virtually and hopefully not from an airport.
Okay.
But
Maybe we can talk there because that's easier. Okay.
Okay.
Other questions? Okay, Rachel, thank you so much.
Thank you.
Good luck with your travels. But
Thank you. Thank you, everyone. Bye.